So we've been talking about limits and like how limits can behave and how limits are handled. And just as a little bit of review, there are many different types of ways a limit can not exist. In this first case here, the limit coming in on this side is much less than the limit coming in on this side. The right-sided limit and the left-sided limit do not agree, so we would say the limit doesn't even exist in that situation. Sometimes on the left-sided limit, the function seems perfectly well behaved, but then on the right-sided limit, things are erratic and insane. In this case, the limit wouldn't even exist. So this is a problem child. This is a problem child. Functions act insane often. As we just spoke about with history, Fourier kind of found a few functions that acted insane like these. And sometimes we could have these vertical asymptotes where the limit as x approaches a from the left is negative infinity, and the limit as x approaches a from the right is positive infinity. Of course, in that case, the limit would not exist. And sometimes the limit is a little bit does exist, but f acts a little bit unexpectedly. So in this case, the limit certainly exists. The height of the function around a is the same on both sides of a, but f isn't defined at a. F has we call it a hole. There is a hole in the graph of f. F has no output at a. And then sometimes a function can have a perfectly well-defined limit at a, but f is defined not as we expect. So f doesn't even exist, or f of a doesn't exist in this case, and f of a does not equal the limit in this case. So here, I'll even write that. F of a does not exist here. And in this case, we have that the limit as x approaches a of f of x does not equal f of a. Okay, so these are in both of these cases, the limit exists and is perfectly well defined, but we would like this to not be the case. It would be much better if we were dealing with a function where the limit as x approaches a of f of x actually was equal to f of a, like this picture right here. So the limit exists and f is as expected. So there's no jump at a, and f also exists at a. So notice in this case, we have that the limit as x approaches a of f of x is equal to the output of f at a. This is so nice, and these functions here are so nice and well behaved that we give them a name. We give them a designated name. We call this, we say that f is continuous at a, if this is the case, okay? And that is the name we give these nice, well-behaved functions that behave as we expected. The function output matches the limit there. Now, this sentence says something mathematically, so I wanted to kind of remind us what that would say. Let's take another arrow. Let's go like this. In other words, f is continuous, and sometimes, and I will often abbreviate continuous as CTS. So this says f is continuous at a if, so, or if and only if, really. So f is continuous at a if and only if for each epsilon bigger than 0. All I'm doing is I'm translating this sentence into nice epsilon delta language. That way we can actually prove some theorems. For each epsilon greater than 0, there is some delta bigger than 0 such that. So notice in this sentence, up until this video, this used to be an L. So in this case, I don't have an L, I have an f of a. So where we see L in the original definition of a limit, I'm going to replace that with f of a. And we're also going to get to do something else, another slight change. So we would have that f of x minus f of a is less than epsilon whenever 0 is less than x minus a is less than delta. But in this case, we actually, the old theory for making sure that, or the old reason for making sure that x does not equal a, in other words, the distance from x to a is bigger than 0, is because we did not know that f of x had an output. For instance, in this case right here, f of a does not exist. So we don't want to allow x to be equal a. But in this case right here, we actually, part of the whole point is that we know that f of a actually exists there. So I think we're going to be able to amend this sort of definition when it comes to continuity and erase this part because we are okay with x equaling a in this case. So we're going to erase this. And this is our definition, official mathematical definition for continuity. So f is continuous at a if and only if this holds. All right. Now, put simply, this is also a perfectly valid definition for continuity at a point. All right. Really, really crucial. Now that that is established, we can start talking about just immediately some theorems. You guys notice that continuity is defined by a limit, which means we have the limit laws that tag along with this new definition of continuity. We know how limits behave. And since continuity is defined by this sort of limit equaling the function value itself, we have also some laws that we know about continuous functions. So this is from our results from calculus page. You guys all have it on Canvas. All of these are true. If we know that f and g are both continuous at a, then the sum of those continuous functions is also continuous. And I'll give a hint right here. This is from our limit law. I think it's limit law 4, okay? So that's easy peasy. Similar right here. This one right here would be from LL3. So hopefully you have the results of calculus page in front of you. I didn't upload it on this one. That would have been helpful. But this is an immediate result of LL4, which has already been proven. Same thing here. A constant, a number times a continuous function will make a new continuous function. The product of continuous functions is continuous, and that is directly from the limit law. I think that would be limit law 5, okay? The quotient of continuous functions is continuous, provided that the denominator doesn't equal 0 at the point in question. That's LL6. Okay, so these are immediate, what I call corollaries, or proofs that immediately follow from other results that we get to tag along. So we know that the sum of continuous functions is continuous. The product of continuous functions is continuous. Constants are continuous. Things like this. Things are going to get a little bit more interesting, especially with this one right here. In a second, we're going to prove this guy in this video. This is a nice theorem. This is also a way we want to think about continuous functions. This guy right here. I kind of listed these in a weird order because if we know this one is true, then this one follows immediately, like barely thinking. So I'm actually going to prove this one and then leave the proof of this one to you guys if you so choose. I might just verbally do it. What this says, notice this. If you have the limit of the composition of two functions and you know that g here, so let me zoom in here. Oops. And you know that g here is continuous, then what you can do is pass this limit through g. So the g is unfazed. A continuous function is unfazed by the limit. It's not going to behave erratically if you swap the g and the limit here. That's what this part is saying right here. That's really how we want to think about continuous functions. If a function is continuous, then this limit can pass straight through the function. If g is continuous, then the limit can pass through g, and we only would have to worry about taking the limit of the function on the inside. Okay, this is a really important result, and we're going to spend some time today proving that, but I wanted to mention other things first. Any function, because of the limit laws, any function of the form f of x equals some sort of polynomial in the numerator divided by some other polynomial. Notice that the degrees of these polynomials are not necessarily the same. Any function like this is going to be continuous over its domain. This is immediate from these continuity laws, the CLs that I just showed you. So this would be CL1, CL2, CL3. CL1 says the sum of continuous functions is continuous, etc. For example, I listed some examples here. If you have any sort of polynomial like this, so this is a fourth degree polynomial, that's going to be continuous over the real numbers. It's continuous over its domain, but there are no domain restrictions here. We're never dividing by 0, and we're never taking square roots of negative numbers. So this is continuous over the reals. Same thing here. This is a 112th degree polynomial, also continuous over the real numbers because there's no domain restrictions. What we're dividing by is 4. In this case right here, we have a polynomial divided by a polynomial. This is continuous over its domain. There are 2 spots where this denominator could equal 0, and that's at plus or minus square root of 7. So it's continuous at each number other than plus or minus 7. So it's continuous over its domain. Here's another random example. Here is a polynomial with a real coefficient. Also perfectly continuous because we have this is the sum of pi over 2, that's a constant, definitely continuous, minus the polynomial x. And the sum of 2 continuous functions is continuous. This is continuous over all real numbers. So this is very powerful. We were just given a whole bunch of continuous functions. Any polynomial we know to be continuous, and any sort of rational function is going to be continuous over its domain. Okay, so we do have to be a little bit careful. Make sure we're not dividing by 0 or taking square roots of negative numbers. All right. I think the next thing we want to do is prove that theorem. Yeah, okay, sweet. I have this makes my job easier if I pre-write everything I want to do for the video. Okay, so check this out. If g is continuous at b, and the limit as x approaches a of f of x is equal to b, then I have this thing I was just talking about where you can pass the limit through the continuous function, and only focus on the inside part. Okay, so this is going to be really powerful for us, and we will definitely use it. We will both prove it and use it in today's video. Let's go to the proof. Let epsilon be bigger than 0. Okay, since g is continuous at b, we know there is some delta g, I'll call it delta g, as in this is the delta that accomplishes something for g. There's some number delta g bigger than 0, such that g of, let's go with u, minus g of b is less than epsilon as long as the distance between u and b is less than delta sub 1. Okay, so I want to make sure we understand what that says. So literally, if triangle minus b is less than delta sub 1, that implies that g of triangle minus g of b is less than epsilon, okay? If, I don't know, let's go with smiley face. If smiley face minus b is less than delta sub 1, that implies g of smiley face minus g of b is less than epsilon. I'm really trying to emphasize what this whenever means. If this is accomplished, no matter what u is, if this is accomplished, this should be delta sub g. Let me fix that. If this is accomplished, I don't care what u is, I don't care what that thing is, then this is accomplished. I know that delta exists, this delta that I grabbed exists because g is continuous at b. Since g is continuous at b, I know this delta exists, but this delta accomplishes something. This delta, this should be like maybe a delta sub b. Bad notation. Or delta, just delta 1. Don't get it too complicated, I guess. Yeah, so that delta definitely exists. Whenever anything gets close enough to b, then g of that thing is close enough to g of b. In particular, g of f of x minus g of b is less than epsilon whenever we can force f of x to be close enough to b. But here's the thing. We know that the limit as x approaches a of f of x is equal to b. That means for any epsilon, I can force f of x to be close enough to b. How close? Epsilon close. So I'm saying something weird. This is a delta, but I think I'm about to call it an epsilon. I know the limit as f of x approaches, as x approaches a of f of x is equal to b. That means any epsilon can be met with a challenger, including this epsilon. So what I'm going to say is, therefore, since the limit as x approaches a of f of x is equal to b, we know there is some delta sub 2 bigger than 0 such that f of x minus b is less than delta sub 1. So again, I want this to happen, but I know I can make this happen by choosing a new delta. This is kind of like our epsilon, okay? So this is the epsilon for the f of x limit. So I'll even write like a epsilon bigger than 0 in like a thought bubble. Whenever 0 is less than x minus a is less than delta sub 2. Okay, so this delta right here comes into play right here. If I force x close enough to a, delta 2 close, then I know f of x is close enough to b, delta 1 close. But if I know delta f of x is close enough to b, delta 1 close, then I know this is the case, okay? But if I know this is the case, then actually that proves what I'm trying to prove, that this is the case, okay? So this is what I just showed. Therefore, g of f of x minus g of b is less than epsilon whenever 0 is less than x minus a is less than delta 2. And notice what we just said. If this is the case, if x minus a is less than delta 2, then this is the case. But if this is the case, we know that this is the case whenever that's the case. So anyway, we did it. And our last sentence is, therefore, the limit as x approaches a of g of f of x is equal to g of b. And that's the same thing as the limit, or g of the limit as x approaches a of f of x. After all, the limit as x approaches a of f of x is b. That's given in the problem statement. And we did it. Okay, that's really powerful. We know that we can pass the limit through continuous functions. That's how I want us to really think about continuous functions. You can pass limits through them. All right, really important. Again, that's what we just proved. We proved that limits can pass through. The limit and the continuous function can swap orders. That's very powerful. Okay, next result. Okay, so this is kind of like a pedantic, semantic sort of result, but I do think it's really important, especially for our next theorem. There is another way to express this. There's another way to say, and this is more, like I said, this is more like, do you really understand what this says? Notice if x is getting really close to a, then f of x gets really close to L. Okay, so that's what this says. But another way I could say that is, as h gets really close to 0, the quantity from either side of 0, the quantity a plus h gets really close to a. So this kind of is replacing x, all right? And h approaches 0. H is kind of like, we want to think about that as the distance from x and a, or between x and a. So as the distance between x and a shrinks, x, or f of x gets really close to L. But a way to do that is say, let's just crush the distance itself. So label h as the distance from x to a. As that distance shrinks to 0, this quantity f evaluated at a plus h is going to get closer and closer to L. Okay, so these are saying the same thing, and I think it's intuitively true, but I wanted to show why it's definitely true by the definition. And again, this is a little bit more of a semantic game, so I'm going to go both directions. Suppose, so I'm starting with this forward direction. Suppose the limit as x approaches a of f of x is equal to L, and I'm also going to let epsilon be bigger than 0. Then there is some delta bigger than 0 such that f of x minus L, the distance between f of x and L, is less than epsilon whenever. So this whenever is really understanding what that whenever means is really the crux of this argument, of this whole proof. Whenever the distance between x, and I don't care what x is, that's crucial here, x minus a, the distance between x and a, is less than delta. Okay. I'm going to kind of do a little bit of a, well, I guess I can do it in this proof. In other words, let me really emphasize what this means. F of star minus L is less than epsilon whenever star is close enough to A. Okay, so that's true for any star. In fact, f of smiley face minus square, I'm very intentionally coming up with nonsense here, but this is still true. That is true whenever smiley face minus square is close enough to A. Okay? It doesn't matter what I replace this thing with. This x is a dummy. Like, nobody cares about what that thing is. But I know that if it's close enough to A, then this is accomplished. That's definition of the limit. But let me choose one that's a little bit more pertinent to what we're trying to say. In other words, f of A plus h minus L is less than epsilon whenever 0 is less than A plus h minus A is less than delta. Oh, shoot, but that says the same thing as, in other words, f of x, or excuse me, f of A plus h minus L is less than epsilon whenever 0 is less than, okay, so we have an a here, but then I subtract an a, h is less than delta, and of course, this says the same thing, as 0 is less than h minus 0 is less than delta. In other words, a combination of this guy right here, this part right here, since epsilon was arbitrary, okay, epsilon began to be arbitrary, we noticed that we can force this to be close enough to L, this close, whenever the distance between h and 0 is close enough to delta. That says the same thing. In fact, I'll really write this. Therefore, or I'll say like that literally means that literally means that the limit as h approaches 0 of f of a plus h is equal to L. Okay. Now, I'm not going to go the opposite direction just to save time on this video. It's going to be a very long video if I keep doing this. So what I just did is I proved this direction to this direction. But hint, hint, going from this direction to this direction, it's the same semantic argument. Just pull this nonsense. Really believe in what we're saying this right here with the whenever. X is just a placeholder. It could be a star. It could be a smiley face minus square. In particular, it could be an a plus h, okay? So this is true at the exact same time that this is true, and this is true at the exact same time this is true. In other words, another way we could say this is the limit as x approaches a of f of x is equal to the limit as h approaches 0 of f of a plus h, okay? Now, sometimes this limit is the best way to do it, but sometimes this limit is the best way to do it. And we now have this tool that we can go back and forth. If this limit is not obvious, then let's go to this limit. In particular, we're about to use that result to show that every single trig function is continuous over its domain. We're going to start with sine. So all trig functions are continuous over their domain. So I'm going to start with this. Sine is continuous at each a in the real numbers. In other words, so this is the result I want to start with, and we're going to use some trigonometry to show that if sine is continuous, then cosine is continuous. If cosine is continuous, then tangent must be continuous, and all these other famous trig functions. Besides, barring the inverse trig functions, because we're going to have to talk about those a little bit later. But in other words, what this says is the limit as x approaches a of sine of x should equal sine of a, okay? So that is what continuity means. This says sine is continuous. That's what that says, continuous at a. So here, let me actually clean this up a little bit. I should write for each a, for each real number a. But using this theorem we just proved, that says the same thing as the limit as h approaches 0 of sine of a plus h is equal to sine of a. And that's what we're going to use. So if we can show this is true, then we will have proven this. Sine is continuous at each real number a. All right. Let's also recall this. Recall. Things we already have. The limit as star approaches 0 of sine of star is equal to 0. We've already proven that. We used the squeeze theorem video, proved that. And we also know that the limit as star approaches 0, that's a 0, of the cosine of star is equal to 1. That's also proven in a previous video. We're going to have to use both of those. But this is a pretty streamlined proof. So let's do it. Proof. Let A being real number. Don't care which one. The domain of the sine function is all real numbers. Then the limit as h approaches 0 of the sine of a plus h is equal to the limit. Okay, let's see if we know our trigonometry. H approaches 0. Let's see if I know my trigonometry. We got sine of a times the cosine of h. All right. And I'm bleeding into my other sort of space here. So let me actually do this. This is equal to the limit as h approaches 0 of sine of a. Oh, that's an alpha. Sine of a times the cosine of h plus the sine of h times the cosine of a. Okay. Now let's see. This is equal to the limit as h approaches 0 of the sine of a times the limit as h approaches 0 of the cosine of h plus the limit as h approaches 0 of the sine of h times the limit as h approaches 0 of the cosine of a. So I just use limit laws. The limit of the sum is the sum of limits, as well as the limit of a product is the product of limits. Okay, but we recognize these. This limit, well, actually, check this out. This limit, what is sine of a going to do as h does? Who cares? Sine of a is simply a number. H is the thing that's moving. A isn't going anywhere. A is simply a number. So I think sine of a is simply going to be a number, and I can use LL1 to say that this is simply sine of a. Now this guy right here, the limit as h approaches 0 of the cosine of h, oh, that's this guy right here. I don't care what this thing is, h or star, who cares, but that's going to be 1. And then we have plus this guy right here. That's the same as this right here. That's 0. Times, who cares? Because it's 0, as long as it's not infinity. It's not. Giving me sine of a. And therefore, sine is continuous. Easy peasy. Okay. Let's do this. Quick proof. Cosine is continuous. Check this out. This is even easier. This is actually, no, maybe not easier, because I actually also have to use this theorem for this one, okay? So I now know that sine is continuous, which means that I can swap the limit with the sine whenever the heck I want. Okay, so that's powerful. Let's go back over here. This is a fun one. I like this. Cosine is continuous. So we hope at A, I should say at A, at any A in the reals. So the limit as x approaches A of the cosine of x, we are hoping that this equals cosine of A. We hope that is cosine of A. All right. So let's see what it is. Well, here's the thing I know. That's the same thing as the limit as x approaches A. Let's do a complementary angle identity. Anybody? Sine of pi halves minus A. Excuse me, minus x. Okay, so in general, pre-calculus, something we have to remember is the cosine of x is always, always, always equal to the sine of pi halves minus x. Those are always the same thing. in the same way that the sine of x is the same thing as cosine of pi halves minus x. But this is the helpful one because we know sine is continuous. So this is equal to the sine of the limit as x approaches a of pi halves minus x. Okay, so because we just showed sine is continuous. All right, but wait a second. This limit is easy. This is one of those plug it in limits because this is a polynomial in x, okay? So what that means is I can replace x with a super easy. That's also just immediate limit loss. So this is equal to the sine of pi halves minus a. Oh, but that's equal to the cosine of a. And what were we hoping for? We hoped that this was simply the cosine of a. Check it out, sure is. Easy peasy. Homework, quote unquote. Show tan, secant, cosecant, and cotangent are all continuous over their domains. So all of these have a little bit more of a pill when it comes to their domains. They're all quotients, right? But we know that the quotient of continuous functions is continuous, and we have that both sine is continuous and cosine. We just showed cosine is continuous. So very powerful. We now have handed to us all trigonometric functions and all polynomials and all rational functions and all roots. I haven't mentioned this yet, but all roots are also continuous over their domains. Really powerful. A few other things I have to prove before we get done with today's video. We're actually making really good progress. It's going to be one of the shorter videos. And one of the things is continuous functions preserve sign. Okay, so here's what this one's saying. I'll read it first, and then I'll kind of decode it to a little bit more simple terms. If f is a continuous function, or excuse me, if f is continuous at a, and I know my function is positive at a, then there's actually going to be a little bit of a bubble around this value where f of x is positive in that entire bubble. Okay, so let me draw a picture. I'll use green. So I have some sort of function right here. Oh, here we go. I have to draw continuous functions. An easy way to think about a continuous function, if I haven't said this yet, is you can draw the function without lifting your pen. Okay, so that's like the basic calculus way to think about a continuous function. So we have a here. Notice I wanted to draw a continuous function, so I didn't lift my pen. And notice that f of a is bigger than 0. What this theorem is saying is I can choose a little bit of a bubble around a such that all f values, including f of a, are all going to be above 0 if I choose x values in this bubble. So notice in this little bubble, and I grab an x from this little bubble and I plug it into my function, the function is going to be positive in that interval. This one is a function that's kind of really well behaved, but let me kind of do one a little bit more erratic, maybe something like this. Okay, so f of a here, let's zoom in. F of a is still positive. Oh, here's a. Can I still find that bubble? I think the answer is yes. It's just a much smaller bubble. So if I beamed this up sort of, all of these f values, right? They all are above 0. So here, let me kind of make that a little bit better. Oh, that's cool. If I grab x from this bubble, I'm going to call it a delta bubble. then f is positive. There. Okay. So, and the reverse also works. For instance, if f is negative for a very small amount of time, you can find this tiny little bubble where, so here we go right here. You can always find this little tiny bubble around the a value such that all these f values are negative if I choose the x values from that tiny bubble. Okay, hopefully this is intuitively true. The continuous nature of f is really the thing that makes this possible. And this proof is really kind of adorable. So let's go over the proof. If f is continuous at a and f of a is positive, okay? Then there's a bubble around a delta bubble around a, such that f of x is going to be positive if I grab any x value in that bubble, okay? So there's some delta bigger than 0, some distance away from a, such that f of x is going to be positive whenever the x values are within the delta bubble. Similarly, if x is negative, if f of a is negative, then there is some delta such that f of x is also going to be negative as long as that x is close enough to a. Delta close. All right, let's see a proof. I'm going to prove only one of them. The analogous idea is, maybe I will prove both here. Suppose f is continuous at a and f of a is bigger than 0. Then there is some delta bigger than 0 such that the distance between f of x and f of a is less than, I want you guys to fill in the blank, whenever the distance between x and a is less than delta. This can be literally anything. Okay, I want to say that. Well, anything positive, okay? Why can this literally be anything? Because I know f is continuous at a. Since f is continuous at a, if you have in your brain that this is epsilon, that's great. That's going to be my epsilon bigger than 0. But what I want us to know is that since f is continuous at a, then we can find a delta given any epsilon. I don't care what that epsilon is. As long as that epsilon is bigger than 0, then a delta will be able to be found. So epsilon could be 7. Epsilon could be 1/3. Epsilon could be pi, okay? So any epsilon bigger than 0 can be met with a delta, including this one. Notice f of a is bigger than 0. So f of a itself could act like our epsilon. Let's check it out. Okay, something we have to remember. The absolute value says something. We want to show that f of x is bigger than 0. Okay, so that's our goal. We want to show that f of x is bigger than 0 whenever this occurs. But this sentence, this is our goal, right? This sentence says something else. Well, there's not something else, but there's another way to rewrite this sentence, and that is that negative f of a is less than f of x minus a, f of x minus f of a, which is less than f of a. Okay, so that's definition of absolute values, or I guess this is because there's another way to write. We've gone over this in class, but absolute value of star is less than triangle if and only if negative triangle is less than star is less than triangle. Those say the same things. They're synonymous phrases. They're paraphrases, I guess. But guess what? Adding f of a to each side of this, that tells me 0 is less than f of x, which is less than 2 times f of a. This part right here, I really do not care about, because this part right here, or here, well, I'll just say that. This part right here, I don't care about because this is what I wanted to show. I wanted to show that f of x oops, wrong color. In other words, f of x is bigger than 0 whenever 0 or x is close enough to delta. Okay. That's what I wanted to show. So I did half of it. We found the delta bubble in this situation. We showed that this delta bubble could occur. So this would be a plus delta, and this is a minus delta. And if I evaluate f at any of those x values, it's going to be bigger than 0. So this is the x-axis. X equals 0, or y equals 0 here. And you can imagine that that's, no matter how severely f is like aggressively bigger than 0, you can always find that delta value. We just proved it. But what about in this case? What if f of a is less than 0? I'll give a hint, and then I'm going to move on. I'm going to try to keep this video short. Now suppose f of a is less than 0. Well, then choose, actually, I think I could do it fast, yeah. Choose delta bigger than 0, such that f of x minus f of a is less than, okay, so we want to choose a nice delta, a nice epsilon. We still know that f is continuous at a. In this case, if f of a is less than 0, then one of the results on our order and absolute value page tells us that that means that negative f of a is bigger than 0. And we know that for any number bigger than 0, any epsilon bigger than 0, we can always find a delta. So I'm going to replace, again, this is my epsilon. But in this case, very awkwardly, but my epsilon is negative f of a. And of course, that says the same thing as f of a is less than f of x minus f of a, which is less than negative f of a, whenever the distance between x and a is less than delta. And of course, adding f of a from all sides, or to all sides, add f of a, add f of a, add f of a. That tells me that f of x is less than 0 whenever x minus a is less than delta. And that's what we wanted to prove. Those delta bubbles, that's what that theorem is about. That's going to be really important in next week's, or in the next video, the bonus video for this week, proving the intermediate value theorem. One more thing. If f is continuous at a, then there is some delta such that f is bounded above on the interval on the delta bubble. In other words, if f is continuous at a, then f is definitely bounded in some bubble around a. So let me kind of draw what this says. So here's a. Maybe f does something like this. So here's f of a. What this theorem is saying, I can make this delta bubble. Okay, so this would be a minus delta, and here's a plus delta, such that f of x, so all of these values right here, are less than some other value. That's what bounded means. Maybe I should define what bounded means. F is bounded on an interval if f of x, bounded above on an interval if f of x is less than m, or I should write it like this. If there is some real number m such that f of x is always less than that real number m for each x in the interval. Okay, so the interval in question here is this delta bubble. F of x is clearly going to be less than this purple line up here in that delta bubble, which says that f is bounded on that delta bubble. This f is bounded over this delta bubble. And you can try to, you always, when you're given these new theorems or these new results, you try to break it in your head. Honestly, that's what mathematicians do. They convince themselves it's true by trying to break it. That's what mathematicians do. That's kind of like the intuition of Bolzano. Well, Bolzano was kind of just attached to truth. He wanted to make sure that we were very delicate with logic and good definitions and good rigor. Fourier kind of just sparked fire on everything in the mathematical world. He was more of a physicist. Anyways, it was a fun history video this time. So I'm going to try to make this worse. What if f looks something like this? Try to make an unbounded f. Something like that, maybe. And so, and we're getting close to some, perhaps, like, asymptote. So let me fix this a little bit. Okay, so here's my new f of x. Now notice in this case, this can't be a right here because f isn't continuous at a. F of a would have to exist. But any value before this, so maybe, I don't know, x equals c or something. Any value before this can be treated as a f is continuous at that value. Okay, so if this theorem were to be true, we have to be able to find a delta bubble, yeah, such that f of x is bounded in that delta bubble. Okay. Now f is getting arbitrarily steep, but we can always make this delta bubble such that f of x is bounded. So here are the restricted f values in that delta bubble. But notice that that yellow line is less than this purple line. All of those f values, the yellow f values, outputs, are less than this big number m. Okay, so we want to think about this real number, the m in the real numbers, as a very large number. Okay, so if f is continuous at a, then there is some delta that creates a delta bubble for which f is bounded above. F of, oh, I wrote it right here. Former self, nice job. F of x is less than some number whenever x minus a is less than delta. Okay, this is not too bad. Proof. Suppose f of x, or f, is continuous at a, then there is some, by definition of continuous at a, delta bigger than 0, such that f of x minus f of a is less than whatever the heck we want whenever x is close enough to a. How close? Delta close. Again, this is my epsilon, but we know f is continuous at a, okay? But this is my epsilon. But since I know that f is continuous at a, I can use any epsilon. How about 1, even though it literally does not matter? It could be any positive number, any positive epsilon. Oh, but that implies that -1 is less than f of x minus f of a, which is less than 1 whenever x is in this delta bubble. Oh, by the way, I'm going to rewrite this so that it matches sort of the proof. Bounded above on the interval a minus delta to a plus delta. This, all x values that accomplish this are precisely the same x values that are in the interval a minus delta to a plus delta. Okay, so I'll say this again. This says exactly the same thing as this. Those are the same phrase, just written differently, okay? But they have the same meaning is really what I mean. So you guys probably see how the proof goes. I'm going to add f of a to both sides of this part of the equation, plus f of a. That tells me that f of x is always less than 1 plus f of a, which is simply a number. So that's some number whenever x is in this interval. And that's what we wanted to prove. F is bounded above on the interval, this interval right here. So I'm going to write that. Therefore, F is bounded above on a minus delta to a plus delta, which means that all continuous functions, we call this locally bounded. And that's going to be really important for when we prove something called the extreme value theorem. And we'll do that next time. Thank you for joining me.